So when you are asked to find the molecular formula from molar mass and elemental analysis, your spidey sense should be tingling, okay? Because this question is not just going to test you on whether you can write an empirical formula, it's going to test you on whether you can remember what the definition of a molecular formula is. And sometimes we can get so caught up in doing calculations, empirical formula calculations, they can take a hot minute now, can't they? So remember the empirical formula is defined as the smallest whole number ratio of elements in the compound. It is not the same as the molecular formula. So molecular compounds can be humongous, okay? And sometimes they can have multiple repeats of the empirical formula for the molecule as a whole. So the molecular formula is the formula of the entire molecule. And remember, when we have covalently bonded compounds that form like these molecular compounds, a molecule is a discrete unit, okay? So there's like a chunk of this particular molecule. So the way to do this is, first of all, you have to work out the empirical formula, but then you are going to compare the molar mass of the empirical formula to the molar mass of the entire compound. If they're the same, then the empirical formula is the same as the molecular formula. The molecular formula may be larger than the empirical formula, never smaller, right? Cannot be smaller, but it can be larger. Okay, so if the molecular formula is larger than the empirical formula, you need to work out how many times the empirical formula goes into the molecular formula. Spoiler alert, it's always an integer, otherwise you've done it wrong, okay? And that integer will tell you how many repeats of the empirical formula there are to make the molecular formula. So you just times the empirical formula by whatever number you get, and then that will give you your entire molecular formula. And the number one thing I see people doing wrong with this question is just forgetting to do that final step, because it's so time consuming and fun doing empirical formulas. So hopefully we all remember how to calculate an empirical formula. Okay, so you're just going to take those mass percentages and say, if I had 100 grams of this stuff, then I've got X grams of carbon, hydrogen, and oxygen in this case, so 40.91 grams of carbon. Use the molar mass of carbon to work out the number of moles of carbon. Rinse and repeat for however many elements you have in your compound. In this case, we've got 3, so 40.91 divided by 12.011 gives me 3.40604 moles of carbon. Again, you don't have to have a huge amount of sig figs, okay? Because eventually we're going to end up with integers, okay? So hydrogen 4.58 is the mass in grams. The molar mass of hydrogen, 1 mole of hydrogen is 1.008 grams. Again, please use the ALEKS data tab if you're actually working in ALEKS, just because it can be a bit fussy about sig figs, etc. All right, so I get 4.54 blah blah, I don't even know, 365 moles of, it was hydrogen, right? Okay, and then lastly, but not least, oxygen. We have got 54.51 grams. 1 mole of oxygen weighs 15.999 grams. Okay, so 54.51 divided by 15.999 is 3.40708 moles of oxygen. Okay, so the little trick then, if we are trying to force this to be integers, okay, you can probably see, well, the carbon to oxygen ratio is 1:1, but what's going on with hydrogen? So to make it easy for you, especially if you're doing exams and stuff, the trick is divide through by whichever element has the smallest number of moles, and that is going to force one of these to be 1. So the carbon and oxygen are going to be 1 in this case because they're identical. I know 40708 is not exactly the same as 40604, but to like 1 decimal place, we're good, okay? And that's all we need for smallest whole number ratio. So 4.54 divided by 3.406 gives me 1.33. So we have like 1 1/3, okay? So we're going to need to multiply by an integer to get rid of that 1/3. The integer is going to be 3, right? 1/3 plus 1/3 plus 1/3 gives me 1, okay? So 1 times 3 equals 3. 1.33 times 3 is going to be 4, and then 1 times 3 is going to be 3. So my ratio is 3 carbons to 4 hydrogens to 3 oxygens. So I could write my empirical formula. Let's make sure we are happy with this being the empirical formula. I'm going to have to label that just to make sure. So subscript C, subscript 3, H subscript 4, O subscript 3, and sometimes people get carried away in like, oh yeah, I've done it right. But we have to work out the molar mass of the empirical formula, empirical, which is C3H4O3. So let's do it. 3 carbons, 3 times 12.011, plus 4 hydrogens, 4 times 1.008, plus 3 oxygens, 3 times 15.999 equals, I don't know, I'm going to have to pick up my calculator. What have we got? 3 times 12.011 plus 4 times 1.008. Sound like the speaking clock. Plus 3 times 15.999 equals 88.062 grams per mole. So now compare it to this sucker up here. What have we got? So this is our molar mass. One thing is not like the other, okay? So to work out how many times the molar mass of the empirical formula goes into the molar mass of the molecular formula, we're going to do the molar mass of the molecular formula divided by the molar mass of the empirical formula. That only makes sense if you were listening when I said it, right? Otherwise, it's just like, what does that stand for? It's too much to type. So that is 176.12 grams per mole divided by 88.062 grams per mole. Again, like nearest integer is good at this point. So 176.12 divided by that is going to be 1.99999999. I'm going to call that 2. Okay? 2 is good. All right, so that tells me there's 2 repeats of the empirical formula in the formula unit. So, bum, 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 draw roll, please. My molecular formula is going to be C6, because we're timing by 2, H8O6. So let's write those in as nice little subscripts. So the C3 times 2 is C6, the H4 times 2 is going to be H8, and then the O3 times 2 is going to be O6. Sorry, that looks a bit horrendous. C6, H8, O6. Okay, so I guess it would be a good practice to do another one. Let me clear my drawings. Here we go. All right, so carbon, hydrogen, nitrogen. Let's see what we got. So I don't know what we got until we do it, okay? So carbon then, 58.77 grams times 1 mole. Carbon over 12.011 grams equals, going quick and dirty on this one now because we've done it a few times, 12.011 equals 4.8930 moles of carbon. Rinse and repeat for my other friends, which is hydrogen and nitrogen. So hydrogen 13.81 grams times 1 mole of hydrogen is 1.008 grams, and that is going to be 13.81 divided by 1.008, 13.700 moles of hydrogen. I just missed the button there, apologies. And then lastly, nitrogen, we have 27.42 grams. Every mole of nitrogen weighs 14 point, what is it on this one, 007 grams per mole. So 27.42 divided by 14.007 gives me 1.9575 moles of nitrogen. It's going to be a fun one. Okay, so to get this smallest whole number ratio, I'm going to divide through, in this case, by the number of moles of nitrogen. So that's going to force my nitrogen to be the 1 in the ratio. Okay, so equals 1 mole of nitrogen. All right, so what about the carbon then? 4.893 divided by 1.95759. I'm sure this is going to be fun. 2.4995. I'm going to call that 2.5 moles of carbon. Okay. Big C, please. My goodness. And then last but not least, 13.7 moles of hydrogen divided by 1.95759 gives me 6.998. I'm going to call that 7 moles of hydrogen. So my empirical formula is going to be C subscript. Oh, sorry, I didn't multiply through by an integer. I was just going to do it in my head, and I shouldn't do that. I've got to multiply it all by 2, right, to get rid of that 2.5. So it's going to be 5 moles of carbon to 7 moles of hydrogen. No, 14 moles of hydrogen to 2 moles of nitrogen. My bad. So that's going to be C5, H14, N2. If I can draw that semi-neatly. 5, 14, yes, just about, N2. So then we need to work out the molar mass of the empirical formula. Remember, that's what we were doing, right? So molar mass of C5, H14, N2 is going to be 5 times 12.011 plus 14 times 1.008 plus 2 times 14.007 equals, dum dum dum, drum roll, while I type this all in my calculator. Ooh, the suspense is killing me. Is it going to be the same as the molecular formula? Who knows? It is 102. Oh, look at that. 0.181. So in this case, I'm not going to do any further calculations because hopefully I can eyeball. If I divide my molecular mass of my molecule by the molecular mass of my empirical formula, I'm going to get 1. So the empirical formula is the same as the molecular formula in this case. And that happens sometimes, okay? So sometimes the empirical formula will be the same as the molecular formula, okay? So that was a fun one to find, okay? So just get more practice of that. The key is remembering the difference between molecular and empirical formulas.